So, good evening, Nandana and Vinay. Can you hear me?
Good evening, sir.
So my voice is clear, right?
Yeah.
Okay, so if you remember, last week we started from this uniqueness theorem and went into surface equivalence principle. So maybe I hope you have looked into book or anything. Otherwise, I'll repeat this once for the sake of recapitulation. So the first of all was like, what was the purpose of uniqueness theorem, right? So the question was, if we have a source, what are the sources? Electric source or magnetic source? Current density in terms of J and M, right? So for that, we have to generally calculate what is the field outside a region. In some region, what is the field E or H? Okay. So the question is, if you have to solve a partial derivative equation. That is the what Maxwell's equation and all. From that, you have to solve it, and you can get multiple solutions from that. So the point was like, how do you get a unique solution? What are the conditions for that? So that from these sources, what are the field you get, the solutions you get, then the solutions will be unique. And uniqueness theorem says that there are three conditions for this to be unique. So one is that in this boundary of this source, boundary that contains these sources. Okay, these current source or magnetic sources, they are contained within a volume. Okay, and on this volume, what is the boundary, surface boundary? So they have to be either specified by tangential magnetic field all over the surface boundary, or tangential magnetic field of H over all over the boundary, or the third option is this, some part of it tangential electric field and the rest of it tangential magnetic field. Okay, so I think this portion must be clear from last week's discussion.
Yes, sir.
Yes, sir.
Okay, so now let's move to the next slide, what is surface equivalence principle of the or Huygens principle. So the thing is like, what was the purpose of this? Purpose is, we have a source somewhere, in the picture if you see, inside the volume V1, we have a source and that is bounded by the surface S. And in the outside boundary, outside the surface, in the volume V2, we have to calculate the field U1 and H1. Right? I hope you can see the field U1 and H1 outside the surface. So the question is, how do we simplify the problem? How do we calculate the U1 H1 without calculating the whole area? Okay, if you take everything into account, it may be very complicated, or the computation time may be more, much more than required. So to simplify the problem, we create an imaginary problem from our actual real problem. So this imaginary problem says this surface S, it should create some equivalent surface so that this will generate the same field U1 H1 as if there was no surface, only J and M was there, and you have to calculate from J and M, solve the Maxwell equation and get U1 H1. So this equivalence theorem says that you should have equivalent problem that gives you U1 and H1 outside. So now what are the actual sources? Actual sources are, just like antenna or transmitter. So in that case, we have either current sources, current density J or magnetic current density M. Okay. So they are replaced by some equivalent sources. So these sources are actually fictitious or imaginary. That will be placed on this surface S. Okay. So these equivalent sources will create equivalent same field E1 and H1 outside this boundary. That you remember. It has to be outside the surface S. Now the thing is, uniqueness theorem says that in the surface S, if we know the tangential electric or magnetic field completely, then the field outside E1 and H1 will be unique, right? That is what we want. We have to confirm that what we are getting has to be unique, right? It is the same all the cases. So that is why the uniqueness theorem will be handy here, or will be helpful in this case. So now what it says, how do we get it? This field outside and surface E1 and H1 is obtained by, on this closed surface, we place some suitable electric and magnetic current density on this surface, S. So that you see in the second picture. In the rightmost picture, this MS and JS, these are the imaginary sources that we place on the surface. How do we calculate that? That will come to later. Okay. This JS and MS are the imaginary sources. Now it says, the current densities are selected so that the fields inside the closed surface are zero and outside are equal to the radiation produced by the actual source. So now our what is our objective? Objective is to get the U1 and H1 outside, right? So we don't care about what is actually happening inside the surface. What is inside surface? That is E and H. E1 and H1, right? Whatever be it, as long as outside we get the same E1, H1, we don't care about what is happening in the closed, enclosed volume by surfaces. So that we have to, our objective is E1 and H1. We don't care about what is going inside. So that's why we have to make imaginary surface such that the field radiated outside should be same. And now how to simplify the problem? This surface is in our control, right? Because everything is imaginary. It is only for calculation we are imagining that this surface can do. So now for this, we will select mostly a PEC or PMC boundary on this, either electrical conductor or magnetic conductor that can enclose this surfaces. So that makes is easier because the tangent PEC or PMC has the conditions, right? It will be either tangential electric field will vanish or tangential magnetic field will vanish. That's why this calculation will be easier. Okay, that is the purpose. That's why this surfaces we will imagine as a either PEC or PMC. Now we will look into where in which case it should be PEC and which case it should be PMC. Now in the in the bottom portion of the slide, you see something in the bold line. So this, remember that JS and MS are imaginary sources, and even the surface S, it is also imaginary. And why we require that? It is introduced so that the equivalent problem will yield the same field outside the imaginary closed surface. That is, we should get the U1 and H1. Okay, now you tell me what are your questions here, which are must be having many questions here. You ask questions. If you don't have questions, then I will ask you questions. You must have questions. You can hear me, right? Hello?
Yes, sir. Yes, sir.
Yeah. So, yeah, please ask questions. What is not clear?
We understood the theorem.
The theorem I did not state it yet. Theorem will come in the next slide.
Okay.
This is just the introduction. Yeah.
Okay. Means from uniqueness theorem, the field outside is derived like that, sir.
Yeah. So from the picture, you tell me.
Mm.
From the picture, you tell me what do you actually want to calculate? What is the component you want to calculate?
This E and H field, no? E1 and
What are the
H1.
components? It is written in picture, right? Yeah. Tell me. Yes.
Sir, here we are trying to get the unique solution. right?
No, yeah, unique solution is okay. Unique solution of what?
Unique solution of unique solution of
I mean, what is the solution? What solution of what? What I'm trying to solve?
unique solution of Maxwell's equations of the field.
Yeah, that will come. And yeah, so this Maxwell equation, now you will express in terms of what? What are the components you have?
E H.
No.
No.
So,
Maxwell.
yeah, you tell me what are your sources? What is your real sources you have? Real. What is the real problem?
Sir, here is there any real source? Like,
Yes.
did
That
they
is what I'm
mentioned
asking.
any real source?
Yes. There are real sources, right? That is only we are trying to make equivalent problem. What is our actual problem? That you tell me.
Our actual problem is like to making equivalent with the volume 1 with the volume 2, E field
No,
and H field.
that is equivalent problem. No. You tell me the real problem. Forget about all the equivalent problem and what is the
Problem
main
is like
problem?
having the real source and imaginary source.
Yeah, what are the real sources here? That you tell me. Actually, you see, there are two pictures. The left side picture shows the real problem, and right side
J and
pictures.
J and M are the imaginary sources.
J are in, they are in both pictures, right? They are a subscript of J. You tell me which one. Here, do you see here in the second line, given the electric and magnetic field source is Ji and Mi? That is what I told you, right? In Innings theorem.
Okay.
This is the problem. See, that's why I'm telling, you have to first understand what is the actual problem. Then you can get equivalent problem. From here, do you understand? J and M, these are your
yes, sir.
sources.
Yeah.
Okay.
And this is the problem you have to solve through this, Maxwell equation and or the Helmholtz equation. You have to solve that. Solve what? E and Hi. Now in this picture here, in slide, you tell me what is your real source and what is the solution you want to get.
Ji and Mi will be the
Here is no JIMI, right?
on the left side, no?
No, it
Means
is
J1,
J1 M1. Yes.
M1 here. That one.
Yeah. Okay. So these are the real sources. And
Real
what do you
solution.
want to? What do you want to get?
From JS and MS
No.
on the
Okay,
right
that's
side.
okay. No.
Okay.
Don't go to JSMS. From J1 and M1, what do you want to calculate? What would be your solution?
The field around the volume 2.
Tangential field.
Then
No. Tangential
even
field.
and
Tell
E,
what?
it is not clear for me. That is even
E1
and
and
H1.
H1. Yes, it is. Okay. So E1 and H1 in volume 2, V2. You
And
see
volume
V2?
2.
That is what we want to calculate, right?
Yeah.
And
From
inside,
J1 and M1, we need to calculate the fields on V2, volume V2.
V2, right? Yeah. So now, if we forget about the surface S and all this, if you do this calculation through this, the previous slide, these equations, so it will take a lot of computations. Okay. So it will, unnecessarily it will make it very complicated, and the computational time will be very large. So to simplify the problem, we are going to right side picture. This is our equivalent problem. Okay. So here you tell me what are the imaginary sources here? Imaginary sources and imaginary, what are the problems? Here in the second picture. Second picture is the imaginary or equivalent thing.
JS and MS are imaginary.
JS and MS imaginary.
And you see the subscript S is because it is on the surface S, right?
Okay.
Yes, sir.
So this volume 1 is enclosed by these surfaces. So on that we have these tangential sources, Js and Ms. Okay. And yeah, what do you want to calculate here in this using these imaginary sources?
It is also E1 and H1, no? What we will
Exactly,
do?
exactly. Yeah, because that was our ultimate goal, to calculate E1, H1 in V2, right?
Okay.
And then if this is the question, then what about E and H inside V1? Do you see E and H now? Previously in the left side picture it was E1 and H1, and in the right side picture it is E and H. So if this change, is it going to create any problem?
But E and H are without source.
E and H is not without source. Sources we have placed, right? JS and MS are now new sources, imaginary sources. So my question is, in the left side picture, there was E1 and H1 in V1. But here you see inside V1, we have E and H. Then how does it help? If it changes, then how can we get the same problem? How can you get equivalent problem? Yes. Yeah, that question I think you understood, right? That's the question. Huh. So that's why here the thing is like we have two zones. One is V1, another is V2. V2 is our zone of interest where we want to calculate E1 and H1. That is where our equivalent problem will solve. V2. That we don't care about what V1 happens, what happens inside surfaces in V1. As long as our E1 and H1 is same, right? That is what I'm saying. Whatever happens inside is, we don't bother because our goal is to calculate E1 and H1 in volume V2. That is what the equivalent problem is. We are not getting equivalent problem in volume V1. Our problem is equivalent problem in volume V2. That is why we don't bother what is E and H, or it is same or different, whatever it is. Is it understood what I'm saying?
Yeah, sir.
So now, yeah, now the question will come. Okay. So if this is so far understood, then we'll go to next slide. But now you see the main point is how is uniqueness theorem is useful here. Now you tell me why I have mentioned uniqueness theorem here. Why is it required? What is the use of uniqueness principle here?
Actually, from the slide also it is written, no?
Yeah.
That, yeah, if the electric field and tangential components are known,
That is written. I
then
also
the
can see. You tell me in terms of right side picture. In the picture, that is actual problem, right? In terms of picture, you tell me. You explain it.
what I understood is from this JS and MS, that is a source, imaginary sources at the boundary.
Mm-hmm.
Uh,
We want to
from that,
calculate. We want to
we can
calculate E1 and
calculate
H1.
the H1 from the in the volume V2. That is, even the sources are in the boundaries of V1, we can
Mm-hmm.
calculate the fields at V2. That is
Mm-hmm.
the
Yes, okay.
thing.
But what is unique about it? Why is uniqueness principle required? Uniqueness theorem. Is Binay? Yeah.
Sir?
Yeah. Yeah. Tell why uniqueness principle theorem is required here.
Sir, with the help of these imaginary sources, we are uh,
We are going to
as
calculate U1 and H1.
Yes. And the original source in V1 and then these
That you
new
forget. Original
sources.
sources we are not required anymore. Yeah. Now see the question is like if you get JS and MS, so how do you know this? What you calculate from JS and MS and get U1 H1? Is it true or is it unique solution? You again don't know, right?
Yes, sir.
That was the point of uniqueness theorem. How do you know it is the actual solution, unique solution? So from this JS and MS also, if you calculate, you don't have any idea if this U1 and H1 is going to be unique. So how you ensure that it is the unique solution? So for that, this is what in this boundary boundary surface S, you need to specify this. This is what was written in tangential E or tangential H. All these are required on the boundary on the surface S. So that is what we should specify in the surface S. Surface S is the boundary between volume V1 and V2, right? Only this surface.
Sir, here like, I am not getting this. We are using uniqueness theorem to prove equivalent surface.
Yes, yes, yes. We are creating the conditions where we will get the same field or same solution U1 and H1. Or what are the terms and conditions so that
So
the
it will
U1
satisfy that uniqueness principles. So it will
yeah,
justify that
because if
equal
you don't
surface equivalence theorem.
yeah, exactly, you don't satisfy or ensure that, then you don't know this U1 and H1 are, it is the actual unique solution or not. To satisfy that, in the boundary, yes, you have to mention all the regions, either tangential electric field or tangential magnetic field on the surface S. That is what we will look into in the next slide. Is it understood?
Yes, sir.
Yeah. Okay. Now you see the same pictures. You look into this in details. So what are these JS and MS? So far all of this we have mentioned. What is the introduction? Why? What about it? But actual surface equivalence theorem, how do you, is all about how do you calculate JS and MS? You see the values are written there. So how do we calculate that? That is the theorem, right? So now it says, the actual radiating source is obviously current density is J1 and M1 and enclosed by the surface S. And these sources actually radiates the fields E1 and H1 everywhere. So from these sources, if you take, so what are the sources? Like, if you take any antenna, antenna has to feed with some kind of sources, right? Current source or voltage source. So that will create some field outside E and H1. Now we are creating this equivalent problem outside S, U1, H1 outside S. So that says, then how do we get this imaginary sources on surfaces? That comes from the boundary principle, okay? Boundary value theorems, okay? So if you take boundary between, interface between two regions, one has field boundary between V1 and V2, right? One has fields E and H, and another has field outside E1 and H1. Okay, if that is what is there, then the what would be JS? It will be the tangential value of magnetic field. So the tangential value of magnetic, this is plain or simple
Sir,
boundary conditions. Tell.
sir, here they have removed that J1 and M1 in second right, I mean, right figure now. Then how
Mm-hmm.
this E1 and H1 is there in V2?
No, I don't understand what.
In figure 2, they removed this original
Hmm.
sources J1 and M1.
Yes.
And how this E1 and H1 is there?
E1 and H1 is there in the outside V2. You are saying.
Yes.
So that is what I told you, in the previous slide. This is the equivalent problem we are creating from the first problem. These sources are imaginary sources. So that is all about equivalence theorem. That is what I am telling you. Even if you
Okay,
remove
by
this,
introducing this MS and JS, we are getting
uh,
E1 and H1.
H1, we are not getting. We have to get. That is all
We
about.
have to get, yes. Yeah,
We are creating equivalent problem of the left to right, so that even if you remove this J1 and M1, it does not care. Only if you know this equivalent sources JS and MS, from that you can create U1 and H1 in V2. That is the equivalent principle all about.
no, I got.
You understood or not?
Yes,
Right?
sir.
Now you're saying like how it will be equivalent. That question you can ask. Even though if you remove J1 and M1, how it will be equivalent? That is what it says in the theorem. So you see how JS and MS is calculated. Now do you see how JS and MS is calculated? Yeah. You tell me how this is calculated. JS and MS values. Do you understand how JS and MS values are calculated?
Yes, sir. They are separating both.
What? Now I think, see, this is the just plain basic electromagnetics. Okay, you have the boundary conditions between two normal components of electric field and magnetic field. We had four boundary conditions, right?
Sir, can you repeat? My network is some issue.
I am asking, how do you calculate this JS and MS? There are two equations. Do you see JS and MS has values in terms of a Carl equation? Carl.
Yeah.
Yeah. So do you understand how it is coming? This is basic boundary value
Boundary.
in electromagnetics between volume V1 and V2. This is the boundary, right? If you have boundary, then what happens? How do you get this? Tangential field, tangential values of magnetic field, how it is, it has a condition in boundary value. There is one of the boundary conditions in terms of relation between tangential value of magnetic field and current density. Do you remember that? This is simply that. Do you remember or not the boundary theorems, boundary value problems in electromagnetics?
Yes, sir. Electric boundary and electric wall boundary.
Yeah, exactly. Now can you relate with that? See the MS, the JS is easier to understand, but MS is actually not a real component. So if you can understand, MS is also same as JS. For the sake of calculation or sake of easier calculation, we just introduce it. MS is the magnetic current density, although it does not actually really it exists. It does not really exist, but we take the equivalent thing, as this tangential value of magnetic field is J, so that we take tangential value of electric field. Let's introduce a new name. That is what people have done. They are calling it MS, magnetic current density. Although it is not a real entity. It is not a real thing available in nature. Tangential values of electric field is called magnetic current density. So the same way as the electric value boundary problem and magnetic value boundary problem. So from this equivalence theorem, this says that as long as your boundary value problems are same, you ensure this boundary remains same, then the problem will be equivalent. Left and right problem will be equivalent because this boundary you have taken imaginary surface S, and these boundary principles are remaining same. JS and MS comes from the boundary, ensuring the boundary. So that's why this E1 and H1, you see, there only we have included it, E1 and H1. So it will be obviously outside, it will be same. Yeah, ask me questions. What are your questions on this? See, the thing is like, if the surface encloses this, volume V1, as long as, boundary comes what? Boundary problems come because, there are boundary and something comes from, something crosses from one medium to another medium, right? So boundary value theorems ensure that this, quantity, this crossing between the mediums, it's same. So as long as we ensure that outside is E1 and H1, that is what we are ensuring, right, in the boundary. We are saying JS is same because it is difference between H1 and H. JS equals curl of H1 minus H. So this nita is the, nita is the outer normal of this boundary S. And with that, if you take curl of H1 minus H, that gives you the tangential component of magnetic value, magnetic field. Neta cross H1 minus H is nothing but is the tangential component of H1 minus H. And if you take neta dot product of H1 minus H, it will give you the normal component of magnetic field, H1 minus H. Is it understood?
Yes, sir.
Okay. So if that is the thing, so now the question is, you see, even we have taken a new field H and E. In the actual problem, there was E1 and H1 in both cases, V1 and V2. But here in the right side problem, inside we have taken E and H. So because what we said in our equivalent principle or surface equivalence principle, it does not matter what is inside V1. We only care about what is V2. That is what we have to calculate, E1 and H1. As long as E1 and H1 is satisfied, you can take anything inside V1. Anything inside V1, that means E and H, you can take any field. Our main goal is to calculate E1 and H1 in V2 in a easier way. Okay, so that's why this E and H, we are taking anything to ensure that JS and MS satisfy with a boundary principle. Now see, why this different E and H we are taking? What is the advantage? That is, so they are saying, the field E and H within S is not the region of interest. Yes, within S is V1. That is not our region of interest. So we can take anything. This is our imaginary problem, and can be assumed that that they are zero in the equivalent problem. So obviously we can, if everything is imaginary inside V1, we will take obviously zero. That will make our calculation easier. So how can we make it zero? We will ensure that this surface. Now I will ask you a question. How can we make this E and H field zero? What can you, modify? What would be your surface S so that this E and H would be zero? Yeah. Did you understand the question?
Sir,
Mm-hmm.
you're telling like inside the volume 1 E and H to be 0. Like
Hmm.
that?
Yes. I'm saying if we make E and H zero, then the calculation of JS and MS will be easier, right? You see,
Yeah.
if that equation, if you put zero, it will be simply neta cross H1, right? And neta cross E1 for MS. So now,
Minus.
yeah. So how do you make it zero? E and H. So what would be your surface S so that E and H would be zero? So this is very simple, right? From basic electromagnetics, from there So what kind of surface, what kind of material will you put on surfaces so that the inside material, it would be zero,
Perfect.
right? That is what is happening.
Perfect
Yeah.
conducting.
So come again.
Conduct.
perfect conducting.
Yeah, it can be, that is what is there. No, it can be either PEC or PMC.
PMC.
Perfect electrical conductor or
Yes.
perfect magnetic conductor. If you put anything inside, field will be zero. E and H should be zero, right? Yeah. So that is what we are going to do. So we are going to do that because it will make our calculation easier. So I told you, right, the surface is imaginary as well as these current sources Js and Ms all are imaginary. So it is all in our hand. What can we put there? We will put obviously some kind of surface S that will make E and H zero, and so our so this version is called Love's equivalence principle. Okay, this Love's principle, it says you see the modified version is it takes H equals 0 and E equals 0. So that way we get the modified values of Js and Ms. So that is all about Love's equivalence principle. You understood? This is the modification of surface equivalence principle. That is actually what is it used, which is useful is this one. Do you understand that?
Yes, sir.
Yeah. No. Yeah. You ask me. Is there any other question? How this is calculated? What are these values Js and Ms?
So these all theorems are used to in for our perspective. It is for why it is calculate the far field or
No. No. There is no far field near field here. This is to calculate U1 and H1. Our equivalent zone is V2 outside the surfaces. So in
that
this
is why I asked.
uh-huh. Yeah. You ask
That,
again. What is?
that's what I asked. Means we are considering the volume two only, no?
Volume
Even the
2 is our equivalent problem. Yes.
even the kind means even our charges or the we are considering one surface and we are calculating the uh, other portion. No?
Yeah, yeah.
That is what for our antenna perspective. What is the significance for these theorems? That is what I asked.
Okay, okay. From antenna perspective, see, yeah. So now that from here, you see, then we have to calculate some field outside, right? Antenna generally we calculate far field or something, even near
That's
field also. Yeah,
okay.
yeah. So from there, if we can, modify these actual sources by these sources,
Imaginary
JSMS,
sources.
yeah. If it gives us, easier problem or simplified problem, that is how it is useful. That is, I will
Okay.
come to that in our problem, how it is used in patch antenna.
Okay.
But so far here it is clear, right?
Surface equivalence
Yes, sir.
theorem will be modified by using this PMC or PEC. That is what it's Law's equivalence principle.
Yeah, exactly, exactly. We calculate, we assume that E and H would be 0. So how can we make this 0? Is that we make we assume a PEC or PMC on the surface S. Okay, then we'll go to the next slide. Yeah, so now we'll see there are two different variations, right? We can take either PEC on surfaces or we can take also PMC in surfaces. So now we'll see what are the different variations of these two and which case we have to take what. Okay. Okay, before that, there if there is any boundary or like any reflective surface or any big conductor PEC or let's say PMC, whatever, if you keep it there, so a source nearby, they will also create an imaginary source or image source. This is this is the picture in the bottom rightmost. In the bottom side rightmost, this picture shows what are the direction of image sources. I hope you have heard about this image sources. If you take positive charge over a conductor, there will be a negative image charge, right, in the opposite side. I hope you have heard about this image sources,
Yes, sir.
right? So they will obviously create like a mirror. So this electric conductor or magnetic conductor, that will act like a mirror. So similar way, here you see there are like two kind of sources. This arrow, single arrow is the electric current and electric current density, and double arrow means magnetic current density. That is what is written. Okay. So now you see it can be either horizontal to this surface or normal to the vertical to the surface. So that way you see how it is different. The top layer shows the actual sources and bottom layer shows the image sources. Now you see the directions, how it varies over. If you take a electric source, that would have some configuration for image. Or if you take a magnetic source means magnetic current density, J, M is the magnetic current density, and electric current density is J. Okay, that will have some other configuration. I think, do you notice that the direction of arrow is very important, and the I modified this thing as I made a rectangular, red color rectangular enclosing this electric and magnetic, that you notice specially because in our sources over surface, yes, these are all tangential sources. That is why these are important for us. Understood, right? What I'm saying?
Yes.
Yeah. So only this red rectangular boxes you notice. What are the tangential sources? Because in our over our surface, JS and MS, what is our equivalent sources or imaginary sources? They are tangential. So now the thing is, now let's look into this, for PEC case. We took the null field within the imaginary surface. Null field means E and H, we took 0 inside in V1. And S is replaced by either PEC or PMC. For PEC case, what happens? If we have, in the actual case, we can have both JS and MS, right? But do we need both JS and MS? We don't need. That is what we will go. This is a further simplification. Why we don't need? So now let's see. If we have a electrical conductor and on top of this you place a tangential electric field or magnetic field. That means J and M, they are the sources, electric source or magnetic source. They will also have image sources due to this PEC or PMC, right? Now what is saying, you see, image current of JS is in opposite phase. That is what you see here. In the bottommost picture, you see the direction of, in case of electric, horizontal electric, direction changes, right? Image source and actual source, you see they are in opposite direction. Do you see that? What I am talking about? Do you see it?
Yes, sir.
But for magnetic case, you see they are both the horizontal magnetic
Same.
sources same, right? Yeah. So that is how it is useful now. You see now you see. If you take image current of Js, that is in opposite phase. So that's why if you take both Js and an image source J dash S, let's say J prime S, they will calculate it and they will be in opposite phase. So actual contribution due to both of them will cancel out for E1 and H1 calculation because they are in opposite phase. So their contribution will be cancelled out for E1 and H1 calculation. That is why JS does not, over a PEC, does not radiate into this unbounded medium. So only MS will be significant because MS, you see, the both are same direction, they will not cancel out. So even so, from this Laws principle over PEC, we will consider only MS. That is what you see in the picture, top side picture A and B. B is for PEC, we have only MS, no JS. Is this point clear? This is very vital. You think about it and then, yeah, just for a minute you think about it. Picture A and B in the top. You see, for A is the normal Laws condition, Laws principle, and for a PEC case, what will happen? That is what shows in picture B.
Yes, sir.
Is clear? Is it clear so easily?
Okay. Which means while considering the PEC, the tangential electric field components will be cancelled.
No, how it is
No,
cancelled? That is it clear, and why
it
it
is
is not?
okay. Because and the magnetic field will be added up. Uh,
Yeah, why? Why?
is
That is what I'm saying. Yeah.
okay. Why it is because when they are added up, these are in the opposite directions. Electric fields are in the opposite, and
Added up
magnetic.
what? Added up of which component you are saying? What is added up?
Magnet.
Electric field and magnetic
E and H.
E and H. E field will be cancelled and
No.
uh,
Why cancelled? Yeah. E and H will be cancelled. That I understand. E1 and H1 you will not have any contribution. But because of what?
JS is in opposite.
JS is opposite. Okay. JS what? Image current. That is what I'm saying. Image
image.
current of JS. So all this happens because of the image current of JS. But
Okay.
image current of magnet MS does not cancel out because
Cancel.
they are in same phase.
Same.
Okay. So if that is the case, and now how uniqueness theorem is useful here? Uniqueness theorem said you need to specify either tangential electric field or tangential magnetic field, any one of them, over the entire surface S. That you have to specify. Then only you can uniquely calculate U1 and H1. So now if we take MS, that MS is what? MS we calculating from neta cross E1. Neta cross H1 is nothing but tangential component of electric field. That if you mention over the whole surface, then obviously you can calculate U1 and H1 uniquely. Okay, is that understood? If we mention MS over the entire surface, that means is by default we specify the tangential component of electric field. So that gives us E1 and H1 uniquely. Okay, is that understood? So this is the second point. B. A and B is the first point and B is the second point. Okay, so B is the second point says why the uniqueness theorem is useful here. What is the essence of uniqueness theorem here? Understood, right? Yeah.
Yes, sir.
Yeah. So now from this you see the top right side. Okay. So before that I will see one thing. See, now you tell me for electrical conductor, what would be the values of tangential electric field? Forget about this principle. From basic electromagnetics, you tell me for a perfect electrical conductor or electrical conductor, what is the value of tangential electric field?
0.
0, right? Yeah,
Zero.
0. But here, if you see, here do you see, we have what is the tangential electric field value here?
Here also the electric field is 0, no?
Here, what is the tangential value of electric field? What is in this our problem? B. Picture A, picture B. What is, tell me from here? You see, right? This is the neta cross E1. Neta cross E1 is the tangential value of electric field. That is what I told you, right? From
Yeah,
here,
okay.
neta cross means it is the cross product. Neta is the outer normal. You see, if neta is the outer normal, if you take a normal cross product with this normal value and electric magnetic field value, so what you will take? Cross product will give you a what component? I hope you remember the dot product and cross product. If you take cross product of two vectors, you get what? This is the perpendicular component of neta, right? Vector neta, you will take perpendicular component. Is it not? It is true or not?
Yes.
So perpendicular component of neta is what? Tangential component that is on the surface. Understood? If you take cross product, because neta is the outer normal from the surface case. So from that, if you take the cross product from neta cross h1 minus h, it will give you the tangential component on surfaces. Tangential component of what? Tangential component of this magnetic field h1 minus h. Is it understood?
Okay, sir.
Now here you tell me what is the tangential value of electric field here.
Is n cross E1.
So that is ms, right?
MS.
Nothing but the magnetic current source ms. That is not zero here. You understood my point? In the actual PEC source, real PEC surface, it should be zero, but here it is not zero. Understood? That is my point. Is it contradicting?
Yes, sir.
You get my point, right? In the real surface, it should be zero, but here it is not happening. So because this is all an imaginary problem, this is not a real problem, right? So you had no equivalence with that. For our imaginary case, we took all this, our surface, current source, everything is imaginary to calculate U1 and H1. So that is what I'm pointing out. You must think about it. So even though it is contradictory, but it does not matter because it's an imaginary problem. Okay. So here everything plays out in this way because this the image sources will cancel out. So it does not help in radiation into unbounded medium U1 and H1. That is how we take it. To get the radiation, we cancel out Js, only take Ms because there for Ms, the actual source and image source, it adds up in phase. Okay.
Yes.
Now let's move to the next slide. Now this is for the PMC, perfect magnetic conductor. Here you see the right side picture, how it is defined. You see, for PMC case, it reverses. Now you see the electrical sources adds up in phase. Actual source and the imaginary source are in different direction. Are in same direction, but the magnetic currents and its image source is in different direction. Understood what I'm saying? Do you see the rightmost picture? Now it is opposite to the previous picture.
Yes, sir.
Yeah. So that is why from Lao's principle, if I place a magnetic conductor over surfaces, now what happens? It will be different obviously. Now you see only Js is there. Ms is cancelled out because their Ms and its image source are in different opposite phase. But the electrical sources are in same phase, so they will be actually contributing to calculation of U1 and H1. So in Lao's equivalence principle for PMC circuits, we will have only Js equals neta cross H1. Okay, so maybe I'll take a 5 minutes break over here. You also take a break and then we'll come back. Huh? You think about it. Whatever. Yeah. Yeah. So are you there?
Yes.
Okay. Okay. So do you have any questions? Is it too much? Too much in one day?
Yes, sir. I mean, lot of in
Yeah, a
and
lot
out.
of things. Yeah. So all these are from Balani's book only. You just can go through once. So some of the things you will not find. I have added it, but the actual mostly it is from there. So this portion I actually missed. How it is useful. So that this right side, top right side picture. Do you see there are three three pictures in one at one.
Yes.
So yeah, so this is how it is useful. Generally, all this we use for aperture antennas. Aperture antennas mostly like horn antenna, patch antenna. That means it has some area in the surface. Not like a dipole antenna, not like one wire or something. Aperture means it has some area surface, right? So like just like horn antenna. So we have some horn antenna, right? In the all four side there are metals, PEC. In the outer layer we have is a open surface, like a dielectric, like a waveguide opening in the outer layer. Okay, so this horn is like all four layers. It is metal, and in the front it is a opening, air opening, right? So they are generally this kind of structures, even in our antenna also. So what do we do with this? We imagine this sigma equals infinite. That means we take PEC surface there, and for this PEC, from this, our principal equivalence principle, we saw what we can take it as the over the surface. We can take our imaginary source EMS equals neta cross E1 minus neta cross E1. That is what we got from left side picture B, right? So what happens if we have any aperture surface or something, any PEC surface? If we, if we have the equivalent problem like this, MS, then if you go to the next picture, the arrow, if you find, follow the arrow, then what happens? Even if you remove that, PEC, then what happens? There is this the image source, right? The image source, if you take, both are in same direction, and from that if you further follow the arrow, so the same problem happens was it both of them adds up and it becomes ms equals minus 2 neta cross, because both source and image source are same, so they adds up. You see how the problem is simplified. So the first case, one thing you must also notice, initially the first picture there's two medium, the right side is mu and epsilon and left side is sigma equals infinite. But now you see the second picture, in the picture in the middle, the moment we take the image source into account, we don't need the sigma equals infinite anymore. So we consider both of them is the same medium with mu and epsilon, because we already took the ms. That is the contribution of PEC. So when we take that, then we don't need to consider two medium. We take that as same medium, mu and epsilon. So it is as if the same source M2ms neta cross 2 neta cross E1 is radiating into a same medium, mu epsilon medium unboundedly. Unbounded means there is no boundary or anything. The same current source or same magnetic current source, it in a one medium only it is transmitting. That is how we simplify our problem using this Love's principle. You understand this? Okay, so now let's come to the application in patch antenna. So what I told you now, all the aperture antennas.
Sir,
Yeah,
so can you repeat once more that?
this one. Can you hear
This
me?
one, yeah.
Yeah. So I am telling from left to right. You see, the left one we had two mediums. One was right side mu and epsilon, and the left side it was a PEC conductor.
Okay.
So now for the PEC conductor, I told you now we will have image source. That image current source is in the same direction or in same phase. So in the medium picture in the middle, we take that image as well as the is image source. And also, when we take the image source, there is no need to consider the PEC anymore. Then we can consider it is as if both sides of the current source is the same medium with mu and epsilon. That is what it shows. And
Okay.
further we can add it as 2ms,
2M.
and that is the this is radiating unbounded medium mu and epsilon.
Okay.
So this similar way, this is used both for horn antenna or all kind of this aperture antennas. Field calculation or far field calculation, pattern calculation you can do from using this. Once if you know the current density on the surface of the antennas, then you can use this to calculate the far field, to simplify your far field calculation. Okay, using this MS. So now, yeah, let's come to our patch antenna. So I hope you still remember what was our patch antenna. So you remember we had 4 sidewalls, and 4 sidewalls we said there are some currents on that surface. There are some tangential electric field and tangential magnetic field. Some of the cases it was there, and some of the boundaries it was not there. So what we said is that dielectric load, it acts like a dielectric loaded cavity, right? Because top layer is metal and the bottom ground layer is also metal. In between we have a dielectric. Dielectric is what is the substrate of the patch antenna. Okay, and so the top and bottom layers are PEC layers, and the 4 layers in the 4 side layers they are called 4 PMC layer or magnetic conductor layer, because we told you, right, so electrical conductor, electrical charge was almost zero, so only tangential component of magnetic field was zero. That is what we have shown you before. Because tangential component of magnetic field is zero, so that's why we call it is a PMC. The side walls, there is no tangential component of magnetic field, because there is no current flow on the no current flow of JS, means electric current flow from top to bottom. This is negligible because the substrate height is so small. There will be no electrical current flow on this substrate. That's why from our boundary condition we know JS equals neta cross H1 minus H. So from if current is zero, so from boundary condition we know tangential value of magnetic field will be also zero. If that is the condition for PMC. PMC says tangential value of magnetic field will be zero. So all the side walls, it behaves like PMC walls. Okay. So now that PMC walls, you see in the picture in the middle, there is no current. JS equals zero, only MS is there. So now you see how we are getting to the Law's principle. Initial problem, there was JS and MS you can consider. But in our patch antenna, actually, JS is zero. Only MS is there in the side walls. So that is how, we take it as, in the third picture, we get the equivalent problem of Mx equals 2 neta cross E1. If we take it as a boundary, and then this boundary, it adds up. It's the same thing here. This picture top right side, I told you, no? If you add it up, source and its image source, it becomes 2 neta cross E1. The same thing is happening here. So yeah, let's read what is there. So it says that from equivalence principle is neta cross HA and magnetic current is neta cross E1. That is there obviously. And E and HA is what? E and HA is electric and magnetic fields at the slots. That means in the 4 side walls. If that is the case, then the most of the charge concentration and current flow remains underneath the patch. It becomes under, you remember there are 2 mechanisms of current flow in the cavity mode. In the cavity mode, so there's like, repulsion mechanism and attraction mechanism. So only the attraction mechanism was, having the contribution, and repulsive mechanism was having almost no contribution. So from that we have shown that, so the most current density will be underneath the patch, and in the surface outer layer the patch current will be zero. So JT is the current on the top layer, that is zero, and also the current in the side layers, that also becomes zero. JS is also zero. So that is why it becomes only the tangential value of electric field, or that is also called MS, magnetic current source, remaining in the side walls. So from that, if you take the presence of ground plane, from using that thing, you can calculate. It should be MS, actual current density, which contributes to radiation outside. Outside is our equivalence principle, zone of equivalence principle, where we want to calculate our field. If you want to calculate far field or radiation pattern, anything, we want outside, right? So for that, we take this MS and also its image field and image current and add up, and it becomes 2 neta cross E1 at all the side boundaries. Okay, is that understood how it is here? How we came from the second to here, how we are using the Gauss principle, do you understand? Because in our ground plane we have a PEC, right? And on top of that we have a image current source. So obviously that image will act like will also have an image current due to PEC. So that will add up and will give us the 2 neta cross E1.
Yes, sir.
Yeah. This is exactly coming from this picture. This one. PEC boundary.
PEC, okay.
So the same thing we will use this principle, equivalence principle, to calculate the far field from the patch antenna. If you don't use this, it will be very complicated. Now you see, using that, how we simplify this. We need only the over the side walls. What would be the horizontal component of magnetic fields? Horizontal component of tangential component of electric field. That is what we need. If we have that, from that we can calculate the the far field. So now this calculation I will not go into. If you are really interested, you see this actual calculation is done in the aperture antenna chapter in Balanis. So they have some formula how to create, how to calculate it. There is some analytical equation actually. Using that you can actually calculate what should be that. If you know the side walls, these sources, from that you can calculate what would be the far field. So before going that, we'll see, so now that we have 4 side layers, 4 side walls, I think if you remember, all of the side walls will not radiate. Now we will see why. Only 2 of the side walls will radiate. Now see, we told you, right, this only across the length L of the surface will have fringing, right? We'll have the fringing field, and that will actually lead to radiation. Now see what is happened. So only these 2 slots are radiating. Rest of these 2 slots, or slots means sidewalls, they are not radiating. So which are the radiating slots? It is across the L. See, across the L, they are separated as L equals almost lambda by 2. So these 2 slots are radiating, which are separated by this distance L or length. So you see here, we in the picture in the middle, it shows #1 and #2. So both of them, they actually lead to radiation. So how that happens? These 2 slots, this current, the electric field you see, they are in opposite direction, right? They are in opposite direction, but the spacing is lambda by 2. Okay. So when you take the equivalence current source M1 across these 2, you see they are in same direction. Although the electric field is in opposite direction in these 2 slots, but if you take neta cross E1, if you see, it is like very simple, right? Electric field is downwards and the neta 2 is in the same direction, of outward direction. So M2 becomes in towards the direction of -z. And the same in the #1 surface radiating slot #1. Neta 1 is the outer normal, and E1 is the direction in X. Here also, if you take minus neta cross E1, the EMS direction becomes in the same -z direction. So that is why it is very simple. If you just see, you will understand. #1 and #2. These 2 slots, M1 and M2, they are in same direction. So obviously, when they lead to the radiation, they will be adding up in phase. So that's why these two are only the radiation, it leads to radiation. But here in the third picture, you see what is happening. If you see the slots separated by width, that means distance W, what is happening? So across this, there are variations. You see, across the length, if you see, the fields have a same kind of variation in two halves. First half is upward and second half is downward variation. So when I'm inside a surface only, these two half cycles will lead to do you see the EMS and these two have a opposite direction current sources. So that will obviously cancel out. So that's why the radiating slots separated by W, they cancel out these magnetic sources in one slot only. So they don't lead to any radiation. So only the radiated slots are separated by L. These two slots, #1 and #2 in the medium, in the picture in the middle. Is it understood how it is also clear from the our principle, Law's principle also shows that because the magnetic current sources are same direction, they will lead to radiation. In the other cases, they cancel out in the same plane only, so they will not lead to. In one picture, it cancels out. In another picture, they does not. So that's why it's the only two slots lead to radiation. Okay.
So in the second picture, it gets added up and means it leads to radiation, and the third will cancel it.
Yeah, right. In the one slot, you see these two slots, M1 and M2, they are in same direction, so they will lead to radiation. But in case of the other one, in a particular slot only, they are in different or opposing directions. That's why they will cancel out the radiation. Okay, now you see how these radiations are calculated. So because of these two slots, so I told you, right? So any aperture antennas, you can actually calculate from these electric fields. So these are the equations you can find out in the chapter there. So it is as if there are two sources and acting like array. Okay, this M1 in slot 1 and M2 in the slot 2. There are two radiating slots. So from for those two, you can have a array factor. So this array factor is the AF, is the formula for that. This is just to remember. This is to have the hint that you can also calculate analytically a similar field. Okay, it is possible for even for a patch antenna. So now you see in the picture in the E plane. So #1 is the contribution for slot 1 and #2 is the contribution for slot 2. And if you add both of this, it becomes total field. The same for H plane. So that way you can calculate total electric field for both of the slots, like E1, #1 and #2. Okay. So now if you calculate that and if you see the in Balaning's book, so there are, you see, this is the actual 3D pattern you can have, E plane and H plane. So in the right side picture, you see how it very beautifully it matches between simulation, measurement, and cavity model. So all this so far we are doing is the cavity model. Why it is important? Because it's like so it matches almost properly with that simulation as well as measurement. And cavity model means so far what we have calculated using analytical equations. If you do these things calculations, you can also get a far field calculations, and that almost matches with the actual simulated results as well as measurement. So these calculations all take into effect of the Law's principle. So where we take these magnetic current sources, and from there using these equations we can calculate E plane and H plane. That is what it shows here. Okay, so I think we'll stop it here today, and from tomorrow we'll look into the quality vector, bandwidth, and other things. Okay, for antenna. So our cavity model of patch antenna discussion stops here. So this is like, it is so important because you can actually have a intuition of how patch antenna works. So what are the walls, radiating walls, how the field distribution was. We looked into how the mode was, mode between the cavity modes, which way. This way actually you can see in your simulation also.
Okay, sir.
Yeah. So okay, then bye for today. We'll see next week. Tomorrow only. Yeah.
Thank
Okay. Okay.
Okay,
Bye.
sir. Good night.